Okay, this is the second lecture in the Chapter 8 Modern Chemistry book. And in this lecture, we're going to be talking about chemical reactions. So we're looking at how elements and compounds can come together and form new substances, or how existing substances can break down into smaller parts. There's a variety of ways that compounds can rearrange and reform. So we're going to look at just a few of those. The first type of chemical reaction is called synthesis, which you'll see right here. Synthesis, the word in general, just means to create. And so in a synthesis reaction, we're taking two or more fairly simple substances and we're combining them into one larger, more complex or complicated substance. So the creation of water, for example, is a synthesis reaction when hydrogen gas and oxygen gas come together to form a larger single substance as water. The opposite of that is called decomposition. That just means to break down, to decompose. So in this case, we have a large, not necessarily large, but a somewhat complex substance that breaks down into two or more simpler parts. So it's the exact opposite of synthesis, although there may be different reactants or different products in these two situations, but the processes themselves are the reverse of one another. The next group of reactions are called displacement or replacement reactions. They are essentially, those two words are interchangeable, and depending on the textbook or the workbook or the lab guide that you're looking at, you may see either term. Our textbook uses single and double displacement, so I'm going to stick with that as much as I can. Single displacement means that there is an element that is just a single monatomic element that is present and reacting with a compound of some kind. And so what happens is that single element replaces a similar element within the compound. So it might be a single metal replacing the metallic part of a compound. It might be a single anion replacing the similar anion within a compound. There are lots of different ways that this can occur, but the name tells you what happens. A single element gets displaced from a compound and a new compound forms. A similar process is double displacement. In this case, we have two compounds that are reacting, and the ions, generally these are ionic compounds, the ions within the compounds trade partners. So the cation from compound 1 becomes the cation in compound 2, and the anion from compound 1 gets a new partner, it gets a new cation, and I'll show you an example of this in just a moment. These reactions are very similar to single displacement, the only difference being instead of having a single element, say element X, plus a compound, something bigger, in single displacement we have a compound, maybe XY, and another compound, say AB. And partners are traded and new compounds are made in the process. Oftentimes, double displacement reactions occur within water solutions or in aqueous solutions because ions are easily dissolvable in many instances, and so they more readily change partners, they more readily pair up when they're dissolved in a water solution. The last chemical reaction type is combustion, and combustion basically means fire. So combustion is when any substance reacts with oxygen to create a large release of both light and heat energy. So we would see that from the outside as the production of fire. Many things can burn. As long as they're burning with oxygen, then that's a combustion reaction. So we're going to look at each of these reactions in a little bit more specific detail. The generic reaction chemical equation for a synthesis reaction is shown here. A plus B yields AB. So again, remember that you have two simple substances They might be individual elements or they might be compounds, and they come together to form a larger, more complex product. Some of the common elements and compounds that would be found in a synthesis reaction, a lot of times you might find a metal, so in this case metal would be A, and oxygen or sulfur could be the B in our little generic equation up there. When that happens, you get a metal oxide or a metal sulfide as your product, right? A metal plus oxygen would be a metal oxide. Metal plus sulfide would be a metal sulfide. You could have a metal reacting with halogens, in which case you would have something like a metal chloride or metal fluoride. And you can have metals reacting with oxides themselves. So it might already be a compound that involves oxygen, like peroxide or something of that effect. And if it were a non-metal oxide, something like SO3, for instance, right? Sulfur is a non-metal, oxygen is oxygen, so that would be sulfur trioxide. We could react that with water to form a larger complex acid, which in this case is sulfuric acid, H2SO4. So there's lots of different ways this can happen, but the formula is very consistent, so it's pretty easy to identify. In decomposition reactions, the formula is just the opposite. So we start with something complex and we break down to two more simple substances. You could start with a binary compound as your reactant, and a lot of times what will happen is we will split these up using an electric current. So you'll have a compound of some kind, we'll run an electric current through it, and it will force that compound to break apart. That process is called electrolysis, or lysis means to break, so electrolysis means to break because of electricity or due to electricity. You can also break compounds down by heating a lot of times. So if you heat, say, something that involves water, right? When you heat, let's say we're heating copper sulfate with the water, this would be called a hydrate. If we heated this up, the water would evaporate pretty quickly into a gas, and you would be left with the copper sulfate behind, and then you could further break that down through other processes. So there's a variety of ways that decomposition can occur. There are oftentimes water, oxygen gas, and oxides of some kind, let's say MgO for instance. Those are very common products during the process of decomposition. So you'll get to where you can look at a reaction and say, oh, we start with one thing, we end up with two or more. This is a decomposition. And then you can look at the products and see, oh, yep, there's water, that's a good sign. There's oxygen, that's a good sign. You'll see the non-metal oxides again, if we're breaking down acids, for example. So you'll get pretty familiar with these and you'll get really comfortable being able to identify them. The next one is single displacement, and I'm showing the two different ways that this can occur. So let me put in our little yield signs. They keep getting lost here. In this first example, I am showing how a metal or a cation of some kind is replacing the cation within a compound. So A is taking the place of B, and then B is now all on its own. Because B is first in this compound, right, there's two parts, and B is the first element, that means it must be the cation. And so it can only be replaced by another cation, and that's what we're showing here. In this second example, there's an anion doing the replacing. So we have Y over here, and it is taking the place of X, which is the second element in the compound, so it must be an anion. And then when the reaction takes place, we have a new anion in the compound, and we have a single anion off on its own. So lots of times, very often, we will have metals involved in these reactions. Metals will often displace whatever the other metal is, right? The cations will replace the cations. Or if it's this example with the anion here, like this one, a lot of times the displacer or the anion that's doing the replacement is a halogen. Halogens are very reactive, as you know, and the top halogen, which is fluorine, is the most reactive, and it can replace any halogen below it. Then we have chlorine, and chlorine can replace any halogen below itself. Then we have bromine, etc. Actually, I think we have iodine next. I don't remember off the top of my head, so ignore that for now. But fluorine and chlorine for sure are correct, and they can replace the element at the top can replace anything below it. So fluorine can replace chlorine or anything else. Chlorine can replace anything except fluorine, and etc. So they're most reactive at the top, and they can only replace less reactive halogens. This is double displacement, and it looks very, very similar to single displacement. In this case, the ions are trading partners. So we start out with two ionic compounds being added together, and the anions and cations each get a new partner. So here, the cation from compound 1 joins with the anion from compound 2 to form a new compound. And the cation from compound 1 and the anion from compound 2 join together to create a new compound, BX in this example. Many times, these reactions are quite fun to look at because many times one of these two compounds will end up being insoluble, which means that they do not easily dissolve in water. And so we'll start with two very dissolvable substances over here, AX and BY. We'll mix them together, and suddenly, rather than having water with these dissolved substances in it, you'll have water with one of these compounds dissolved, which means you essentially can't see it. And then we'll have this other compound where all of a sudden you've got this very obvious solid formation, because that compound, when these two ions come together, they form a solid that does not easily break apart in water, and so you'll be able to see it. That's called a precipitate. It's a very fun reaction, and we will look at some of these in the lab as well as online. You can often have water as one of the products, right? If we have a hydrogen ion and an hydroxide, which is OH minus. So if these guys are part of the compounds up above and they come together during the displacement, then water will form. We can also form gases, all kinds of different gases. So this is a pretty fun reaction type to study. I mentioned this a little bit in the single displacement reaction, but just to recap, the activity series is a description of how reactive or how likely an element is to undergo certain chemical reactions. It's very similar to kind of ionization energy or electron affinity that we talked about a couple of chapters ago, and I see a typo here. This should say gain electrons. We often describe activity of an element depending on what type of element we're dealing with, whether it's a metal or a non-metal. The idea of greater activity for metals means that they easily lose electrons, which we know metals like to do, and those that lose electrons more easily are said to be more reactive. And non-metals, it's the opposite. The metals that gain electrons more easily are the more active non-metals typically. So there's what's called an activity series. It's a general kind of table that shows in order, comparing one element to another, how reactive or non-reactive that metal is. So if you look on page 286 in your book, you'll see this long list of metals, and they're metals from all over the periodic table. They're not necessarily within groups. the higher up on the list, the more active the metal is said to be, and the lower it is on the less reactive. So you'll use that as a source for making predictions. If you have two things in a reaction, you can predict whether or not they will react, or they will trade places, or one of them will be replaced, etc. This is not something I expect you to memorize, but just be able to use. So please come to class with 3 questions that you need clarification on or are unclear to you, and we will move forward from there. Thank you.